Hi guys, I'm Kevin. I joined the department in 2015 following a Royal Academy of Engineering Research Fellowship, and I'm a slightly strange fish in electrical and electronic engineering because I trained in physiology, pharmacology, biomedical engineering, the analysis of the human as a living system, and ironically the analysis of a human living electrical system. I cut my teeth making electrical recordings from cells inside the eye, which is a destination on our journey today. It's not a standard lecture. It's designed to expand your mind a bit about what electrical engineering can be and what it means to us as humans, and how we can use it to help each other. I would emphasize on the way that we have an awesome campus. It's beautiful. The lake is really quite special, and if you get an opportunity to have a wander about, I highly recommend just starting out. You're over here somewhere behind those trees. You can do the circuit of the lake in about 20-30 minutes, and there's loads of squirrels and birds and lots of nice stuff to see. Nottingham's got its best clothes on for you today, so take advantage of that. It does freeze solid in the winter, but not this year, and it's kind of a feature at the heart of the campus. So the reason why it's on the board, though, is because this image represents about half a dozen shots that I took with a big DSLR camera, one of the big ones with the lens on the front that you've probably seen. And I've put it there because by the time I'd finished stitching those 7 or so images together and made one file out of them, the total data in that image represents about the same size as sent man to the moon. The Apollo space mission had less storage and data processing capability on board, both in the vehicle and on the ground, than is represented in that one image, which is on the screen for you today. So things are changing extremely quickly. Electrical engineering is at the heart of absolutely everything, from the technology that allows you to see that image on the screen, to process the data in the computer, to shooting out a bunch of photons from a semiconductor that's in my hand and producing a spot of light that, if I took it outside and pointed it into the night sky, could be reflected from the moon and detected back to us here on planet Earth. So the scope of what we do as electrical engineers is vast. It all boils down to an unusual material called silicon, which is an insulator that man has learned to interfere with by implanting foreign ions in its crystal matrix and causing it to be capable of conducting electricity under certain circumstances. So I'm going to touch today on a couple of things we can use that for. The reason that I'm in front of you at all is because Nottingham is right up there in terms of the applicability of what we do. From both teaching and research, we meld them together. We poach the good students to become researchers, and we embed research in the forefront of human knowledge into all of the teaching that we do. We have everything from our head of department playing with high energy, massive amounts of power in power stations, through to submarines, to aircraft, in my case to microscopes and tiny little biosensors that go inside and interact with the human body. So there are places where you personally can still contribute, and this is where I live. In fact, this is where all of you live in terms of their interaction with the outside world. This is a view of the human eye, and its relevance will become apparent in a second. But basically, we have a hole through the front through which we can see the world. Light arrives to us through that hole, having been bent by the cornea, focused by the ocular lens, which was my tissue that I studied during my PhD, and focused into a sharp image on this tissue at the back of the eye called the retina. The retina is a piece of the brain. Embryologically speaking, there is no difference. The same sheet of cells that gives rise to the brain during embryology gives rise to the eye. These are electrical devices communicating with each other to transduce an image formed by light on some receptors at the back called photoreceptors into a signal which is transduced out via the optic nerve as a series of electrical impulses to the brain, and allows us to see the world around us, to react, to escape predators, to find food, and nowadays to do many other things besides. So my research project during my PhD was to look at the electrical behavior of the cells that make up this organ. They have to operate throughout your life in the absence of a blood supply. And that's kind of interesting because every other piece of your body has blood going through it constantly, because the metabolic demands of the cells need to be met and the waste products produced need to be removed. It turns out, and I was one of the first in the world to actually show in practice, that this tissue operates an electrical system to pump fluid and liquid and ions through itself, and thereby bring in glucose and feed the cells. And if we grow old enough, you'll see at the end of this talk why that architecture is now challenged by humans' ability to keep ourselves alive for decades and decades and decades past our years of reproduction. So, I present that as an analogy for what we can do as humans with our brains to analogize our technology to things that we observe in the world around us. The human eye is basically identical in its layout to a human eye. We have a lens which takes light emanating from an object in the distance and focuses it to a sharp image on a detector array. And that detector array is, as I discussed before, a piece of dumb silicon. How can we use that to build an image? Well, we have to thank for that a gentleman called Albert Einstein. Albert Einstein received the Nobel Prize back in the early 20th century for the discovery of the so-called photoconductive effect. It was not the theory of relativity. That came later. It was well worth the Nobel Prize. Unfortunately, he already had one, and they cannot be awarded twice in the same discipline to the same person. So, Albert Einstein noticed that electrons in any atom, in their normal ground state, are perfectly happy to remain where they are. In a piece of silicon, where all of the bonds are exactly the same and in a very, very low energy state, the electrons are utterly reluctant to move at all. If that crystal has been modified by doping with certain other foreign ions, the process of which you will learn about through our course, they can be induced to possess an excited state into which they can be launched by the small amount of energy of an incoming photon. A photon is a bundle of light traveling in a straight line representing a packet of energy and very little else. So long as that energy exceeds the energy required to lift this electron from the ground state into the so-called excited state, it can be caused to enter a band which is capable of conducting through that material. And those electrons are our business if we wish to build an image using an electrical system. So I'm going to teach you today about two different ways that we have learned to use these photoelectrons, so-called, to build an image. One is by catching them, literally catching them in a bucket and reading them out, a so-called charged coupled device, or CCD. The other is probably in everybody's pocket right now. The phone that I got last month has 3 of them on the front and 1 on the back. A so-called CMOS, or complementary metal oxide silicon process, which operates on a completely different principle. In fact, we let electrons go, and then we build an image from that. So, we also have just about surpassed the engineering hurdles required to count the incoming energy of individual photons interacting with the lump of silicon, both in space and in time, approaching but not breaching Heisenberg's uncertainty principle and allowing us to truly study things down at the level of individual photons, the energy inside which is utterly minuscule, and the achievement of this represents one of the great moments in human history as far as I can see. So, without further ado, here is a camera. Taught by analogy. This is something that we have to do quite a bit in teaching anything, but particularly in the case of electrical systems, it's quite useful to think of them in terms of water, because water can flow, it can be caught, it can be trapped, it can develop potential and pressure, be siphoned in different directions, and if you wish to study the elements of fluid dynamics, you will find that it actually shares a lot of parallels with electrical theory. So here we have a charged coupled device camera represented as a set of buckets left out in the rain. The rain is incoming photons producing an image on the surface of the detector, which is our array of buckets. And these buckets are discretizing a two-dimensional space into a set of literal accumulating reservoirs into which the rain can fall, representing different amounts of light falling in different places. In order to make sense of this, we've put the buckets onto some chain conveyors, which are capable of moving the accumulated water in each bucket from place to place. And this is the basis of a charged coupled device. During the exposure, the buckets fill with rain. They fill with rain to a different extent depending on how much rain is falling on that part. And the distinction between the different amounts is what allows us to see light and dark. At the end of the exposure, we stop the rain. A shutter obstructs the camera, and we proceed to take all of those buckets and, moving the conveyor, tip them one by one into a so-called readout register, which is another set of buckets arranged at 90 degrees. And in the second part of the cycle, that readout register is advanced one by one into a measuring cylinder. We quantify the amount of water in each bucket, And by doing that, and knowing the position in which the bucket was, we can then develop a two-dimensional map of how much rain was falling, i.e. how much light was coming down onto our detector. And that cycle is repeated again and again in order to build up an image. Every single one of those operations gives rise to a frame, and those frames are built extremely, extremely sensitively. These devices represent something like 96% quantum efficiency now. Just about all of the energy that is seen by the sensor is converted into a usable signal. We bought one of these in the lab about a month ago, and I had to sign a bunch of documents promising that I would not export this camera to certain countries because they still represent the absolute bleeding edge of military technology. They were developed to fly at the front of a cruise missile and navigate to targets and so on. Nowadays we use them in the research lab because of their exquisite sensitivity to tiny, tiny amounts of light. And that's my business. So the reason why these cameras are great is because of their sensitivity. The reasons why you don't find them in your mobile phone is that every single time you move charge from place to place like this, you're using energy. And the use of energy, by the time you have many, many buckets and many, many things to move, is not inconsiderable. If you were to have one of these cameras in your mobile phone, the lifetime of that battery would represent it in hours rather than days. Small numbers of hours. And so a new technology was required in order to make something portable and certainly parallelizable as these devices are. And here it is, so-called CMOS camera, or complementary metal oxide silicon camera, which is made on the same sort of production lines as produce CPUs for computers, other microchips. Very, very mature technology that's capable of doing very nice things. And each pixel, or each bucket in the previous analogy, consists of a small and simple circuit. And so what we have is voltage applied to the chip, to which all of these pixel sensors are charged to the same voltage at the beginning of the imaging cycle. By connecting that to the voltage with this switch, we put charge on the capacitor proportional to the voltage. To take a picture, we then expose the camera to light. And this component, a diode, a photodiode, has been sensitized in a certain way such that the arriving photon energy promotes electrons into the conduction band and allows the charge sitting on that capacitor to flow through that device to ground, and do so proportional to the amount of incoming energy. So that cycle is pretty quick, it's pretty simple. All of these little circuits are completely separate from each other, and the voltage across that photodiode at any time can be determined without disturbing the measurement. And that's the key. We don't have to push charge around, we don't have to waste energy. We can have many bites at the apple, and it is this ability that allows modern CMOS cameras to be made extremely small, extremely power efficient, and also to cope with the vastly different amounts of light energy we find in our environment. Some of you will have seen the Attenborough documentaries, which are just getting better and better in terms of this kind of thing. You have a white ice floe with a black seal illuminated by full daylight, and underneath, in the shadow of the ice floe, is coming a killer whale to eat the seal, and you can see all of that in one image, where the amount of photons on the ice floe might be in the millions or even the billions per nanosecond arriving onto the chip, down to the dark areas in the shadow where you have a black killer whale coming up, where the light flux might be 6-7 orders of magnitude lower. And one single device can quantify both of those things to good fidelity at video rate. It's quite remarkable, and it's not finished yet. So, our analogy with the human eye doesn't stop there. We are visual creatures that live in a world made of colours. But silicon is a dumb piece of material that couldn't care less what colour is your photon, so long as the energy is enough to promote an electron into the conduction band, you will have that electron. In order to make a colour camera, therefore, we need an array of colour-sensitive filters, which we manufacture in front of the chip, to provide RGB vision. The reason for that is because we have RGB vision in our retina. We can take red, green and blue as separate channels, the mixing of which produces colour in the world around us. By doing this on a microchip, we can estimate those things separately and present them to the human eye in a way that is intelligible. But in doing so, the images we come out are contaminated to a degree by the method with which they were produced. And each of these images represents something that looks like a dangerous air accident, or perhaps these guys flew into a power pole. Some of you will have taken images like this from a moving car. where everything looks a bit slanty. And there's a good reason for that. These artifacts, so-called, are a function of how the images were acquired. And here we have a contrast between the two different camera technologies that I presented to you earlier. On the left is a so-called frame transfer device, such as a CCD camera, where all of that image is created by leaving the buckets out in the rain. Okay? All of those buckets are being filled at the same time. At the end of the exposure, out comes an image. On the right-hand side, all those pixels are independent. So some of them are being exposed, some of them are being read, some of them are being reset on a continuous basis, creating a cycle which can be run in many places simultaneously on the same chip. But the upshot is that those lines are built one by one with time passing in between. And so if you look at something that is changing in time, you will see some quite strange things. The frame transfer device, so long as you have enough light available to illuminate something, you can pretty much freeze time down to the level of nanoseconds if you have a very, very good device, and literally see something the way it was in that instant. A rolling shutter device, by contrast, as that fan is rotating, that image was being built, and so that fan blade remained in the image most of its cycle. That's not reality, that's an artifact of how the image was created. So for taking a picture of something that looks intelligible to you, you may think that this is a garbage way of doing things, but actually, au contraire. Here is another picture which looks utterly incomprehensible. Here's an aero engine rotating at some unknown speed. The blades look actually physically detached from the device, look like they're flying off, but that's not the case. This is another artifact of the fact that these images are being built asynchronously in time. That engine has many blades and they're rotating at some unknown rate. The difference in frequency between those two events creates a difference frequency, a so-called heterodyne effect, which would allow you, at the end of the degree, to tell me how fast that thing was rotating if I was to tell you how fast those images were being taken. And this kind of trick is used throughout electrical engineering. We play tricks with carriers and frequencies and squeeze information through technical bottlenecks that the pure physics or our pure pedestrian human mind is incapable of comprehending. But once you understand the tricks and the subtlety, you'll be capable of playing these kinds of games with the technologies that exist to build new technologies that don't. And that's basically what gets me out of bed in the morning. So just for the last couple of minutes, I would like to take you on a journey through the eyes of another man and convince you that our eyes also do lie and that there is hope for us as humans in the future. This is Claude Monet, a very, very famous painter, father of the Impressionist movement, so-called. It doesn't show very well here, but he was the master of a technique called pointillism, where the brush was used to draw literal small points, a bit like pixels, to produce highly, highly detailed images in a novel way. And he became very rich and still exists his estate in Giverny in France, where you can go and see this lake over which is a Japanese bridge, which he painted about 20 times during his career. And early in his career, at the turn of the century, this is quite clearly a verdant kind of spring scene. And later in his career, he painted exactly the same scene. And artists change. So this is a pointillist image. This is much more abstract. Styles do change. Seasons also change, and you may think that this is clearly spring, blues and greens. This may well be autumn, falling leaves, reds and oranges and yellows. But no. These were painted at the same time of year, 25 years apart. And this is how that scene looked to Claude Monet. And there is a very good reason for that, which we now understand very well. This speaks to my own background as a research scientist who studied the ocular lens. And this is a medical image taken using a so-called slit lamp, which some of you may have experienced, where the ophthalmologist comes to your eye with a microscope and shines in a beam of light and is able to look at the deep structures inside your eye. And ordinarily, structures that are not that are completely transparent, that don't scatter light, are invisible in this method, which is why we have black areas where the fluid is, inside the cornea of the eye where there's very little scattering, there's very little to see. In a normal eye, inside the lens here, this would be similar. It would be transparent, it would be possible to visualize through that structure, but here we have a scattering object that is colored, floating in space in the middle of that eye. This is what lens cataract looks like to clinicians. And nowadays, humans are capable of treating this disease by going with a needle through the cornea into the ocular lens, emulsifying the material inside using ultrasound, removing that material, and through the same incision without stitches, introducing a small plastic lens which is folded like a tube, which unfurls, fills the space, and produces perfect vision in the eye of somebody with an advanced lens cataract. This is the most commonly performed operation in the world now. If you live long enough, you will need one, if not two of these, because the human eye has a unique tissue, the ocular lens, which grows throughout your life, and it has no blood supply. And eventually this thing becomes so large and so inflexible that it can no longer change its focus under your control, and so we need reading glasses. As that process continues, the inside of the the inside of the lens becomes more and more divorced from external means of support, and the proteins and the cells in the center become this opaque mass, which is actually brown in color, and eventually will make the world look to you the same way that this scene looked to Claude Monet. And the benefit of humans looking at such a problem is that we can build techniques to see what's going on. We can apply our minds to understand what's going on by making, for example, electrical measurements of the thing, and come with not only a clinical treatment to fix the problem, there's nothing wrong with the eye, it's something in the way, but also now we're working on methods which will prevent the problem in the first place, prevent the arrival of this disease process, saving money, saving time, saving quality of life for our aging population. So that's where I'll leave you. This is all electrical engineering, but we have been many places, and I would convince you that it's bigger than you think, and you're going to enjoy it. So thanks very much. It's lunchtime.
Okay, so thanks very much for listening to us. We're going to take you off for lunch now, which is in another building, so I'll call our ambassadors